Black holes have captured the imagination of scientists and laymen alike for centuries. These mysterious cosmic entities, regions of spacetime where gravity is so strong that nothing, not even light, can escape, represent the ultimate frontier of the universe. But what lies beyond the event horizon, that invisible boundary separating the known from the unknown? Today, we delve into the secrets of black holes, exploring how they form, their remarkable properties, and what theories suggest occurs within. First identified in the early 20th century from the equations of Albert Einstein's general theory of relativity, black holes were theoretical constructs until the 1970s, when indirect evidence began to accumulate. The term black hole itself was coined by physicist John Archibald Wheeler in 1967, yet even today, they remain less understood than the stars that populate our night sky. There are three main types of black holes: stellar, supermassive, and intermediate. Stellar black holes form from the gravitational collapse of massive stars at the end of their life cycles after consuming their nuclear fuel. This process often results in a dramatic supernova explosion, where the star's outer layers are expelled into space, leaving behind its core to collapse under its own gravity. Supermassive black holes, often found at the centers of galaxies, including our Milky Way, can contain millions to billions of times the mass of our Sun. Their formation remains a topic of significant research, with hypotheses suggesting they could have formed from the merging of many smaller black holes or from gas collapsing directly in the early universe. Intermediate black holes are a more elusive category, as their existence is still debated. Nevertheless, recent discoveries hint at their potential existence in globular clusters, leading scientists to ponder their role in galaxy formation and evolution. Black holes are fascinating not only for their immense gravitational pull but also for the phenomena surrounding them. Matter that spirals into a black hole forms an accretion disk, an incredibly hot and bright disk of gas and dust. As material in this disk accelerates, it heats up and emits extraordinary amounts of radiation, often making black holes some of the brightest objects in the universe. This radiation, especially in X-rays, can be detected by telescopes on Earth and in space, allowing astrophysicists to study their properties and surroundings. But what happens once matter crosses the event horizon? That is where the science becomes profoundly complex, intertwining physics with philosophical inquiry. The event horizon is not a physical boundary but a region from which no information can escape. In the following chapters, we will explore what theories suggest may lie inside a black hole, including the possibility of singularities, and how quantum mechanics and general relativity might clash in such extreme environments. What can we learn from black holes about the fabric of our universe? The journey into the heart of black holes promises to illuminate not just the nature of these enigmatic objects but potentially the very nature of reality itself. As we set the stage for our exploration, one question looms large: is it even possible to know what happens once we cross the threshold of a black hole? To truly understand black holes, we must first grasp how they come into existence. Stellar black holes, the most common type, are born from the fiery deaths of massive stars. When such a star exhausts its nuclear fuel, it can no longer support itself against the pull of its own gravity. During its life, a star fuses lighter elements into heavier ones, creating energy that balances the force of gravity trying to collapse the star inward. However, once it can no longer fuse elements, the balance tips. For a massive star, typically more than 20 times the mass of our Sun, the end is a spectacular supernova explosion. This cataclysmic event blasts the star's outer layers into space, often creating beautiful nebulae while leaving behind an incredibly dense core. If this core remains above a critical mass, about 3 solar masses, it will continue to collapse into a black hole. The result is a zero-volume point of infinite density known as a singularity, surrounded by the event horizon. But let's not overlook the fascinating life cycle of these giants. Stars like our Sun, which are not massive enough to become black holes, will instead swell into red giants and then shed their outer layers to form planetary nebulae, leaving behind a white dwarf. They simply do not have the necessary mass to create the conditions necessary for black hole formation. On the other hand, the process of forming supermassive black holes is shrouded in even greater mystery. According to current theories, these black holes may have arisen in the early universe, potentially growing through the merging of smaller black holes or the direct collapse of massive gas clouds. This phenomenon would help explain how they could reach billions of solar masses, sometimes within just a few 100 million years after the Big Bang. An intriguing observation supports the existence of supermassive black holes, the detection of stars orbiting invisible objects in the centers of galaxies. For instance, astronomers have tracked the orbits of stars around Sagittarius A*, the supermassive black hole at the center of our Milky Way, indicating its mass is about 4.1 million times that of the Sun. Such findings paint a compelling picture of a universe where immense gravitational forces govern the dynamics of galaxies. Further complicating our understanding is the potential existence of intermediate black holes. In recent years, astronomers have begun to identify candidates for this category, discovered in globular clusters, where dense populations of stars are found. The detection of gravitational waves, ripples in spacetime, has also provided robust evidence of black hole mergers, linking them to the formation of these enigmatic cosmic entities. The formation of black holes is a testament to the dramatic and often violent processes that govern our universe. Yet, as we ponder their origins, we must also consider what happens once these phenomena become established. The next chapter will take us to the heart of black holes, exploring the enigmatic event horizon and what theories suggest may occur beyond it. In the realm of black holes, the event horizon is a pivotal concept that generates both fascination and confusion. Defined as the boundary around a black hole beyond which no information or matter can escape, it serves as a one-way gateway into the depths of spacetime. Cross it, and you're lost to the universe, a sobering thought, isn't it? The event horizon is not a physical surface. Instead, it's a region in spacetime where the escape velocity exceeds the speed of light. This means that any object, whether it's a spacecraft or a beam of light, requires more energy than is available to escape the gravitational pull of the black hole once it crosses this threshold. For example, if Earth were to collapse into a black hole, its event horizon would be just over a centimeter in radius, a stark reminder that size and density are not synonymous. One of the most compelling aspects of the event horizon is its relationship with time. According to Einstein's theory of relativity, as an object approaches the event horizon, time appears to slow down from the perspective of a distant observer. This effect, known as gravitational time dilation, suggests that for someone falling into a black hole, time would feel normal, but to an outside observer, they would appear to freeze at the event horizon, gradually fading from view. This illusion challenges our understanding of reality and perception. Furthermore, the edge of the event horizon is where the laws of physics as we know them begin to break down. Although general relativity predicts the existence of black holes, it does not fully account for the quantum effects that dominate at such extreme densities. This clash of two fundamental theories, general relativity and quantum mechanics, creates a paradox dubbed the black hole information paradox. At the core of this paradox lies a question: what happens to information that falls into a black hole? Some theorists propose that information may be preserved in a distorted form on the event horizon itself, while others suggest it may simply be lost forever. This uncertainty has prompted a significant amount of research, with physicists like Stephen Hawking contributing pivotal ideas that have shaped the discourse surrounding black holes. Despite these complexities, the event horizon remains a tantalizing topic of study, pushing the boundaries of our understanding of the universe. Will we ever unlock the secrets it holds? The next chapter invites you deeper into the gravitational abyss, seeking to uncover what lies within the event horizon, the singularity itself. What lies beyond the event horizon? This question has puzzled scientists for decades, sparking a plethora of theories, each more intriguing than the last. At the heart of a black hole lies the singularity, a point of infinite density where the laws of physics as we know them cease to operate. Current understanding suggests that as matter collapses under extreme gravitational pull, it effectively warps spacetime to an unimaginable degree. The most widely accepted theory posits that all matter and energy falling into a black hole is crushed to an infinitely small point, known as a singularity. Here, gravity becomes infinitely strong, and the known laws of physics break down. But the nature and implications of this singularity remain a mystery. Some physicists, like Roger Penrose, have explored the properties of singularities, showing through mathematical models how they arise from gravitational collapse. However, this viewpoint clashes with quantum mechanics, which suggests that information cannot be destroyed. This leads us back to the black hole information paradox, raising questions about the fate of matter that crosses the event horizon. Some theories propose that the information might be encoded on the event horizon in a manner akin to a hologram, a concept known as the holographic principle, championed by theorists including Juan Meldacena. Another fascinating idea is the notion of wormholes, hypothetical passages through spacetime that could connect distant regions of the universe. If black holes can form into these wormholes, they may serve as gateways for traversing vast distances or even different times. However, such concepts remain purely speculative and require rigorous mathematical frameworks to be taken seriously. Yet, they invigorate the imagination, invoking visions of teleportation and cosmic travel. The quest to understand what happens inside black holes also continues to inspire scientists to develop new theories and frameworks for merging quantum mechanics with general relativity. Researchers are exploring ideas beyond traditional science. Some even propose that the universe itself is a holographic projection. This radical notion suggests that everything we perceive as three-dimensional might be encoded on a distant two-dimensional surface. As we dive deeper into the unknown, we can't help but ponder the implications of these theoretical perspectives. What does it mean for our understanding of the universe? The next chapter will explore what happens when black holes interact with their surroundings, including their role in galaxy formation and how they influence stellar evolution. Black holes are more than just cosmic vacuum cleaners, they play a vital role in shaping the universe. Their gravitational influence affects the formation and evolution of galaxies, stars, and even the structure of spacetime itself. Understanding this dynamic is crucial for comprehending the broader tapestry of our cosmos. At the centers of galaxies, supermassive black holes serve as anchors, influencing the motion of stars and the dynamics of entire galaxies. The Milky Way's own supermassive black hole, Sagittarius A*, is located approximately 26,000 light-years from Earth and has a profound impact on its galactic neighborhood. Research shows that the mass of supermassive black holes correlates with the characteristics of their host galaxies, a relationship known as the M-sigma relation. As galaxies evolve, the interplay between supermassive black holes and their environments can lead to the formation of new stars and the regulation of star formation rates. Black holes also serve as extreme laboratories for studying fundamental physics. Their inhospitable environments push the boundaries of current theories, presenting opportunities to test the limits of our knowledge. Gravitational waves, produced by the merger of black holes, offer insights into their properties and the nature of spacetime. Detecting these waves has opened a new frontier in astrophysics, allowing scientists to observe and analyze cosmic events that were previously invisible to conventional telescopes. Moreover, black holes are suspected to be key players in the evolution of the universe itself. Some theories propose that their formation and growth may have contributed to the large-scale structure we observe today, including galaxy clusters and superclusters. In this way, black holes influence not just the local environment but the entire cosmic landscape. As we observe the universe, we are beginning to understand that black holes might even have a hand in the creation of new stars. As gas and dust fall into an accretion disk surrounding a black hole, immense temperatures and pressures may trigger nuclear fusion, leading to the birth of new stars. This process highlights the dual nature of black holes. They are destroyers and creators, devouring matter while simultaneously being integral to the cosmos' evolutionary process. In conclusion, black holes are far from simple voids in space. They are complex entities that play an essential role in the universe's grand design. Their dynamics challenge our understanding of physics and push us to reconsider foundational concepts of matter, energy, and the structure of spacetime. As we continue to uncover their mysteries, one thing remains clear: black holes are not just the end of the journey but a vital chapter in the ongoing story of our universe. As we transition into the next part of our exploration, we invite you to ponder the ultimate question: are black holes the key to understanding the nature of reality itself? As we delve deeper into the mysteries of black holes, one curiosity remains the most perplexing: the singularity. What exactly is this enigmatic core, the crux of a black hole's being? Picture, if you will, the very essence of gravity concentrated into a point of infinite density. This singularity, framed by our understanding as a mathematical oddity, poses questions that stretch the limits of modern physics. The laws of physics, as we know them, break down at this point. It's an area where the known laws governing time and space lose their meaning, creating a paradox of existence. Many physicists assert that once an object crosses the event horizon, it's on a one-way trip to the singularity. But what happens there? Are we simply obliterated, our existence erased from the universe? Or does the fabric of reality twist into something entirely new? In Einstein's theory of general relativity, the singularity represents a breakdown. However, quantum mechanics provokes alternatives. Could it be that singularities lead to the birth of new universes? Ideas like the Big Bounce postulate that singularities could be gateways, not just cul-de-sacs. In 1971, physicist Brandon Carter suggested that perhaps singularities are not the end but the start of something magnificent. Intriguingly, if we probe deeper into the nature of matter and energy under extreme conditions, might we reveal pathways that connect black holes to the very fabric of the cosmos itself? This idea borders on theoretical science fiction, yet it beckons us to explore further. The implications of a singularity transcend the boundaries of our comprehension. Could they be shadows cast by the edges of our universe, hinting at dimensions beyond our grasp? As we continue to investigate, we must balance between our scientific understanding and the mysteries that seem to defy explanation. With every theory we create, we inch closer to deciphering whether singularities are mere mathematical curiosities or windows into the deep universe's soul, leaving us with an unsettling truth: what lies within may forever remain a mystery. The answer might just lie in our next chapter, where we explore the interactions between black holes and the fabric of spacetime itself. In our exploration of black holes, we now stride into a captivating realm: the interplay of black holes and spacetime. Spacetime, the four-dimensional continuum that underpins our universe, is significantly distorted by massive objects, particularly black holes. Imagine being caught in a gravitational web, where the normal rules of space and time bend and warp around you. As we approach a black hole, the effects of its immense gravity become increasingly apparent. Light itself becomes ensnared, unable to escape its pull. This phenomenon, known as gravitational lensing, can create breathtaking cosmic images, distorting our view of the universe beyond. In essence, black holes act as cosmic magnifying glasses, unveiling distant galaxies and phenomena hidden from our naked eye. But the true marvel lies in how these voids influence the very nature of time. Near a black hole, time slows down significantly. What seems like minutes for someone near the event horizon could equate to years for those far away. This effect, known as gravitational time dilation, was first theorized by Einstein. Imagine a scenario: astronauts orbiting a black hole, venturing closer, only to return aged, while their peers on Earth have experienced decades. It's a mind-boggling concept that illustrates just how intertwined time and gravity are through black holes. Additionally, black holes may also participate in the creation of gravitational waves, ripples in spacetime caused by the acceleration of massive objects. In 2015, the LIGO Observatory made history by detecting these waves from colliding black holes. It was a breakthrough, melding general relativity with observable evidence. Such discoveries not only affirm the influence of black holes on spacetime, but also open new avenues for research, leading many to speculate on the potential for interstellar travel using these gravitational effects. Yet, as we push further into these theories, we are still left teetering on the brink of understanding. With each revelation, we find ourselves wrapped in the eternal dance between reality and the enigma of the universe. With such powerful forces at play, where shall this dance lead? As we delve deeper, we explore the potential for traversable wormholes in our next chapter. With a firm understanding of black holes and spacetime, we now embark on an exciting journey into the realm of wormholes. Imagine shortcuts through the fabric of the universe, connecting distant points in space and time. Wormholes, often described as tunnels through spacetime, arise as solutions to Einstein's equations. The concept is alluring, a bridge across the cosmos that could make the stars accessible. However, these tunnels are theoretical constructs that, if they exist, may have their paths dictated by black holes themselves. The notion of traversable wormholes invites exhilarating possibilities. If we could enter one end of a wormhole, could we emerge at the other side, perhaps decades or even centuries into the future, or light years across the galaxy? This concept, while captivating, is fraught with challenges. First, the stability of a wormhole is under question. Most theories suggest they would collapse quickly without exotic matter to keep them open. Such matter would possess negative energy density, a requirement that currently exists only in theoretical predictions. Even so, the possibilities wormholes present push the boundaries of our imagination. In 1988, physicists Kip Thorne and Michael Morris proposed a model for a traversable wormhole, envisioning it as a viable route for interstellar travel. Despite the hurdles, the scientific community remains intrigued, leading to multidisciplinary research involving relativity, quantum mechanics, and the very nature of gravitational forces. Would navigating such a wormhole allow us not only to traverse space but also time? What impact would this manipulation have on causality? The implications are profound, raising philosophical questions about existence and reality. Still, as we probe these wormhole theories, the universe presents us with stark realities. We remain bound by our current understanding and technological limitations. It's a paradox, fueled by infinite possibilities yet tethered by our finite comprehension of the cosmos. With each inquiry, we tread closer to the edge of discovery. What awaits us on the other side of this cosmic veil? In our final chapter, we will summarize our thoughts and consider the future of black hole research. As we conclude our journey through the realm of black holes, we glance toward the horizon of future research. The world of astrophysics is rapidly evolving, and black holes remain at the forefront of our scientific inquiries. The recent successes of gravitational wave detection have revolutionized our understanding of these cosmic giants. As we continue to explore the vastness of space, the question arises, what will we uncover next about these enigmatic structures? One compelling frontier is the study of supermassive black holes at the centers of galaxies. Observations reveal that nearly every large galaxy harbors a supermassive black hole, including our own Milky Way, which contains Sagittarius A star, a monstrous black hole that weighs around 4 million times that of our Sun. Scientists are now focusing on how these supermassive black holes interact with their host galaxies, revealing insights into galactic evolution and dynamics. Additionally, as data collection and analysis technologies advance, the potential for a more profound understanding of black holes emerges. Projects like the Event Horizon Telescope aim to capture direct images of black holes, an achievement we witnessed in 2019 with the first-ever image of the black hole at the heart of the galaxy M87. Such endeavors continue to push the boundaries of our observational capabilities, allowing us glimpses into the veil surrounding these cosmic enigmas. The future also beckons quantum physicists to merge their insights with those of astrophysics, leading to potential breakthroughs in understanding black hole information paradoxes. Questions linger regarding the fate of information that spirals into a black hole. Does it truly vanish, or is it encoded in the surrounding event horizon? As we ponder these future explorations, we realize that black holes are not simply astronomical phenomena but keys to understanding the fabric of our universe. Each discovery unearths layers of knowledge, challenging our comprehension of existence itself. As we gaze toward the cosmos, let us remain curious, for the universe has much more to tell us. Our quest for knowledge may illuminate not only the structure of black holes but also our place in the grand cosmic tapestry. As our journey comes to an end, we reflect on the profound impact black holes have on our understanding of the universe. These extraordinary entities challenge the limits of our imagination and push the boundaries of scientific inquiry. From their mysterious formation to their intricate dance with spacetime, black holes remind us that the universe is far more complex than we often perceive. What began as a curiosity born of mathematical theories has evolved into a field of extensive research, inviting humanity to explore greater questions about existence, reality, and the cosmos itself. Each discovery related to black holes has not only deepened our knowledge of astrophysics but has also sparked philosophical contemplations about time, space, and our place within the universe. We have pondered the fate of information, the possibility of wormholes, and the paradoxes that pervade our understanding. As we stand at the threshold of exploration, contemplating the future of our inquiry into black holes, we realize that the questions are never-ending. With each step forward, we inch closer to understanding the very nature of reality. The legacy of black holes is more than mere mysteries. They serve as a catalyst for innovation, collaboration, and the unquenchable thirst for knowledge. So as we close this chapter of our cosmic exploration, let us take a moment to marvel at the wonders that lie beyond our reach. The universe is filled with enigmas yet to be unraveled, and through the lens of black holes, we gain greater insight into our own existence. The quest for understanding is far from over, and as we look to the stars, we are reminded that the journey itself is what propels us forward. Black holes will forever be intertwined with our exploration of the cosmos, and who knows what future revelations may await us just beyond the event horizon. Imagine a phenomenon so strange, so counterintuitive, that it blurs the lines between science and science fiction. Stephen Hawking proposed that black holes may not be entirely black after all. They could emit radiation, leading to their eventual evaporation, a process now dubbed Hawking radiation. This concept challenges our understanding of what it means to exist and brings us face to face with the strange marriage of quantum mechanics and general relativity. Hawking's theory suggests that particle-antiparticle pairs can spontaneously pop into existence near the event horizon. One particle could fall in, while the other escapes, creating an observable radiation. But what implications does this have for our universe? For one, this could mean that black holes have a finite lifespan, contrary to the long-held belief that they are endless voids. If a black hole can evaporate, what happens at the point of its demise? Some theorize that the information swallowed by a black hole may be released back into the universe, leading us to re-examine the nature of reality and information itself. This leads us to the paradox: if information can be lost in a black hole, how can the laws of physics still hold? In 2012, the discovery of Hawking radiation was a turning point in black hole physics, inviting debate among the brightest minds in science. What if this radiation could be detected? Could we witness the death of a black hole, unraveling the mysteries of information and existence? The implications don't stop there. If black holes evaporate, could this lead to a universe without them? The question remains, how do we reconcile the loss of information with our understanding of the universe? Hawking radiation doesn't just stretch our knowledge of black holes, it reveals the complexities of reality itself, hinting at deeper truths that lie just beyond our reach. As we delve deeper into the universe's secrets, we encounter dark matter, a mysterious substance that makes up about 27% of the universe. Its essence is elusive, as it does not emit light or energy, making it nearly impossible to detect directly. However, scientists speculate that black holes might hold clues to understanding dark matter. Could it be that black holes are gateways or reservoirs for this enigmatic substance? Recent studies have suggested a potential link between black holes and dark matter, citing the gravitational effects dark matter has on galaxies and the cosmic web. In fact, black holes could help explain the formation of structure in the universe, as their gravitational pull could influence the distribution of dark matter. Notably, a primordial black hole, formed in the early universe, might serve as a candidate for dark matter. If these black holes exist, they could explain the missing mass that galaxies seem to harbor. A study published in Nature Astronomy highlights that these black holes might account for the gravitational lensing observed in many deep space observations. Imagine searching for these primordial black holes in the cosmos, unraveling a mystery that has puzzled scientists for decades. Furthermore, how do black holes interact with dark energy, which makes up about 68% of the universe? This symbiotic relationship between black holes, dark matter, and dark energy could uncover profound truths about existence. Black holes are not just cosmic vacuum cleaners, they might be the keys to unlocking the universe's most closely guarded secrets. The quest for understanding dark matter and its connection to black holes could redefine everything we know about the universe. Imagine standing on the threshold of a black hole, feeling the immense gravitational pull as you prepare to plunge into its depths. This hypothetical journey is more than just a thought experiment, it hints at the very nature of our reality. What would it be like to venture beyond the event horizon? As you approach, time dilates, and distances warp in unimaginable ways. From the outside, an observer would see you slowing down, your image stretched and distorted, never quite crossing that boundary. What would happen next? Beyond that invisible line, physics as we know it becomes unrecognizable. Theories suggest that space and time lose their traditional meanings, they could even reverse roles. You might find yourself spiraling inward, experiencing intense tidal forces that stretch your body, a phenomenon known as spaghettification. The closer you get to the singularity, the more these forces intensify, tearing apart matter at an atomic level. As you continue this harrowing descent, the laws of physics begin to break down. Would you encounter alternate dimensions or parallel universes? The idea of a black hole as a portal is not entirely science fiction. Some physicists theorize that the interior might connect to wormholes, allowing a passage through spacetime to another point in the universe, or even another universe altogether. Yet, if this were true, could we ever emerge on the other side, unscathed? As we explore these possibilities, it's essential to remember that our understanding is merely the tip of the iceberg, suggesting a reality far stranger than we can comprehend. The journey into a black hole raises profound questions about existence, reality, and the fundamental nature of our universe. What awaits us beyond the event horizon could redefine the very fabric of our understanding. Imagine a world where black holes are not completely black, where they might actually emit radiation and lose mass over time. This groundbreaking idea was proposed by the brilliant physicist Stephen Hawking in 1974. He suggested that black holes could emit particles due to quantum effects near the event horizon, a process now known as Hawking radiation. This idea turned the conventional understanding of black holes on its head. For decades, we thought that once something crossed the event horizon, it was lost forever. Yet, Hawking's theory suggests that black holes can evaporate, potentially leaving behind a universe unburdened by these enormous celestial entities. The implications are staggering, prompting scientists to rethink not just black holes, but the very fabric of our universe. To understand this, we must delve into the world of quantum mechanics. In the vacuum of space near a black hole, particle-antiparticle pairs can spontaneously form. When one of these particles falls into the black hole while the other escapes, it results in a net loss of mass for the black hole, leading to the phenomenon of Hawking radiation. But how significant is this radiation? It's believed that for stellar mass black holes, Hawking radiation is minuscule and nearly undetectable. However, for smaller black holes, the radiation would be proportionally higher, potentially leading to their rapid evaporation. This brings us to an intriguing aspect of Hawking radiation, the fate of information. If black holes can evaporate through Hawking radiation, what happens to the information contained within? This question leads us into deep philosophical and scientific discussions about the nature of reality and information. Researchers are actively investigating this information paradox, sparking debates on whether information is truly lost or if it can be recovered in some form. The fate of black holes may not be as final as we once thought. The enduring pursuit to dissect these cosmic enigmas has not only enriched our understanding of black holes but has forced a re-evaluation of our fundamental assumptions about physics. As researchers continue to explore the universe's most profound mysteries, Hawking radiation remains a key focal point that challenges us to redefine what we know about black holes and the elements of our universe. Will the ultimate fate of black holes reveal secrets that transcend our current understanding of time and space? Only time will tell. Dark matter. It occupies about 27% of the universe yet remains invisible and undetectable through conventional means. What if black holes could provide clues about this elusive substance? As we explore the relationship between black holes and dark matter, we may be stepping closer to understanding the universe's dark side. Studies have suggested that some black holes may be candidates for dark matter. In particular, primordial black holes, which may have formed in the early universe, could account for some of the dark matter we observe today. These mini black holes, potentially as small as an atom, would have unique properties. Unlike stellar black holes, their formation wasn't due to supernova explosions but rather fluctuations in density in the universe's infancy. If they exist, they could provide valuable insight into both dark matter and black hole physics. For instance, a study published in the journal Physics Reports pointed to the potential detection of primordial black holes through gravitational waves. This is groundbreaking because gravitational waves allow us a new way of observing the universe, especially phenomena that are otherwise hidden. However, the relationship between black holes and dark matter goes beyond mere speculation. Recent research indicates that supermassive black holes found at the centers of galaxies might influence dark matter distributions around galaxies. These gravitational giants could be shaping the very structure of our universe. When we imagine the cosmos, we often picture stars, planets, and glowing nebulae, but dark matter and black holes add layers of complexity that are still unfolding in our understanding. The mysteries of dark matter challenge our grasp of fundamental physics, and black holes serve as a key to unlocking these enigmas. The ongoing quest to unveil the true nature of dark matter could redefine our comprehension of the universe. As we stand at the precipice of new discoveries, the entanglement of dark matter and black holes beckons us toward revelations that could illuminate the darkest corners of existence. What would it be like to journey into a black hole? This question captures the imagination of scientists and dreamers alike. We often envision the event horizon as a terrifying boundary, but what lies beyond? To embark on this journey, we must first understand the stages of falling into a black hole. As you approach, the gravitational pull would intensify, causing a phenomenon known as spaghettification. This term, coined humorously, describes how objects get stretched and compressed into long thin shapes due to the difference in gravitational forces on opposite ends of the object. Imagine being pulled apart as your feet get closer to the black hole compared to your head. It's a brutal fate for any astronaut brave enough to attempt such a journey. However, let's temporarily push aside the harsh reality of gravity and instead entertain the theoretical perspectives offered by physics. What if instead of annihilation, the journey leads to another universe, into what could be called a wormhole? Some theories suggest that black holes could act as gateways to alternate dimensions, a bridge between our universe and others. This has inspired countless works of fiction, from movies to books, but could there be a grain of truth in this? The mathematics behind it is complex and not fully understood. The concept of a traversable wormhole, as first posited by physicist Kip Thorne, requires a significant amount of exotic matter with negative energy density. Yet, the possibility ignites our imagination. Picture a world where traveling through a black hole is no longer an impossibility but a vivid reality. To illustrate, consider the idea proposed by Thorne and his colleagues in the 1980s. If one could create a wormhole, time travel might also be a possibility. The implications of such a revelation would upend our understanding of time itself. While these ideas remain speculative, they point to the fundamental questions of existence and the universe's nature. What does lie beyond the black hole? Is there a way out on the other side? These inquiries shape our cosmological landscape and push the boundaries of scientific exploration. As we contemplate the destinies of black holes, we find ourselves pondering the grandest questions of existence. What mysteries await us just beyond our current understanding? Perhaps, as we continue to study these enigmatic giants, we will inch closer to answers that could redefine the fabric of reality. When we talk about black holes, we're not just discussing cosmic vacuum cleaners that gobble up everything in their vicinity. We're diving into one of the most fascinating implications of quantum mechanics, Hawking radiation. Named after the brilliant physicist Stephen Hawking, this concept provides a striking connection between quantum mechanics and general relativity. But what is Hawking radiation, and how does it relate to black holes? Hawking proposed that black holes are not entirely black, and they can, in fact, emit radiation due to quantum effects near the event horizon. This radiation arises from virtual particle pairs, tiny fluctuations that pop into and out of existence in what we perceive as empty space. Normally, these pairs annihilate each other almost instantly. However, if one particle falls into the black hole while the other escapes, the escaping particle can be detected as radiation emitted from the black hole. This means that black holes can slowly lose mass over time, which has profound implications for their life cycle. Now, imagine a black hole that swallows a massive star. Hawking's calculations suggest that this process could lead to black holes eventually evaporating completely. Black holes, once thought to be eternal, could actually have lifespans. In fact, for stellar mass black holes, this evaporation process is incredibly slow, taking billions of years. But what about the black holes at the centers of galaxies? Supermassive black holes, which contain millions to billions of solar masses, might take trillions of years to evaporate. Yet, if Hawking radiation is real, it leads to questions about the fate of information. According to the famous black hole information paradox, information that falls into a black hole is thought to be lost forever. But if black holes evaporate through Hawking radiation, where does the information go? This paradox has sparked debates among the greatest minds in physics. Some theories suggest that information is encoded in the radiation itself, while others propose that it exists on the event horizon, a concept known as holography. This creates a fascinating intersection of physics, information theory, and cosmology, with implications that could fundamentally change our understanding of reality. The exploration of Hawking radiation pushes us into the forefront of scientific research, encouraging experiments and observations that may either confirm or challenge this groundbreaking theory. For instance, scientists have considered the use of analog black holes, created in laboratory settings, to study Hawking radiation under controlled conditions. These experiments could shed light not just on black holes, but on the very nature of space and time itself. So, as we unravel the enigma of Hawking radiation, we're not just solving a cosmic puzzle, we're redefining our understanding of the universe. But what would happen to the universe if all black holes eventually evaporated? What could take their place in the grand cosmic tapestry? That's a question worth exploring as we move deeper into the mysteries of black holes and their lasting impact on the universe. As we delve into the dark reaches of space, two of the universe's most intriguing cosmic phenomena emerge: black holes and dark matter. At first glance, they appear as separate entities, but recent research suggests a complex relationship that may reshape our understanding of the cosmos. Dark matter, an invisible substance that makes up about 27% of the universe, is inferred through its gravitational effects on visible matter. While we cannot see dark matter directly, its presence is necessary to explain the clustering of galaxies and the rotation speeds of stars within galaxies. Now, imagine this: what if some black holes are actually formed from the collapse of dark matter? This idea stems from the fact that dark matter particles might interact with each other under specific conditions, leading to gravitational instabilities. These instabilities could create regions dense enough to form micro-black holes. Some theories even propose that these micro-black holes could be the key to understanding the discrepancies in galactic rotation curves, which have puzzled astronomers for decades. In essence, may our dark matter mysteries be tied to the birth of black holes? It's both a thrilling and daunting thought. Additionally, black holes might play a role in the evolution of dark matter itself. When black holes pull in dark matter through their gravitational influence, they may act as catalysts for the clustering of dark matter in the early universe. This relationship hints at a cosmic dance that extends beyond mere theoretical speculation. As we examine this connection, the implications expand. Could black holes actually be the harbingers of dark matter interactions? Researchers are investigating the potential signals of dark matter signatures in the vicinity of large black holes. The hope is to detect unique radiation patterns or particle collisions that could provide insights into the nature of dark matter. The combination of studying black holes and dark matter could open new avenues in particle physics and cosmology, deepening our knowledge of the fundamental building blocks of the universe. And as we venture further into this cosmic mystery, we uncover the possibility of existence beyond our current models of physics, challenging and expanding our understanding of everything from the origins of the universe to its ultimate fate. But if dark matter and black holes are interconnected, what mysteries await us at the very edge of this relationship? How will these revelations alter our comprehension of the universe's structure as we know it today? Imagine being an astronaut on the brink of a scientific revelation. You prepare to embark on a journey toward a black hole, an incomprehensible abyss that warps the very fabric of space and time. As you venture closer, the gravitational forces intensify, pulling your spaceship toward the event horizon. Theories suggest that if you could observe what happens as you approach this cosmic giant, the experience would be nothing short of surreal. Time itself would stretch, causing you to witness the universe outside your spaceship in a bizarrely slow motion, a phenomenon known as gravitational time dilation. From your vantage point, distant stars would appear to elongate and shift colors as they become gravitationally lensed, a spectacular visual dance of the universe unfolding before your eyes. But then comes the moment of truth, crossing the event horizon. At this point, all connection with the outside universe ceases. You are ensnared in the black hole's grasp. What awaits you on the other side? This is where things get even stranger. Some physicists speculate that if you somehow survive the intense tidal forces, you may enter a different universe or experience a singularity that defies our current understanding of physics. Dr. Kip Thorne, one of the leading theoretical physicists, has explored the concept of wormholes that could theoretically allow shortcuts through spacetime. If black holes connect to another region of spacetime, this opens tantalizing possibilities of interstellar travel away from our black hole, if only we could harness such technology. But let's consider a more immediate question: what if you could gather information during this journey? Researchers have begun developing theoretical frameworks around how information might escape a black hole, suggesting that black holes could be a source of unique insights into the universe's most enigmatic secrets. This quest carries us deeper into the heart of black hole research, implying that what lies within may not be purely destructive, but rather a repository of universal knowledge waiting to be unlocked. So, as we contemplate the plunge into a black hole, are we merely facing our end, or is it the beginning of a journey into uncharted territories of existence? The boundaries of understanding collapse when we consider that this journey might reshape our entire cosmological narrative, leading us to astonishing revelations about the nature of our universe and our place within it. As we delve deeper into the cosmos, one of the most perplexing aspects of black holes emerges: the information paradox. This conundrum stems from a fundamental question that challenges our understanding of physics. When an object falls into a black hole, the information about its state, its physical characteristics, seems to vanish completely. This leads to a startling implication: if information can be lost, then it stands in stark contrast to the basic tenets of quantum mechanics, which assert that information cannot be destroyed. Renowned physicist Stephen Hawking was at the forefront of this debate. In the 1970s, he proposed that black holes emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This radiation allows black holes to gradually lose mass and, theoretically, evaporate over time. However, the profound question remains: what happens to the information contained within the matter as it crosses the event horizon? This dilemma has sparked various interpretations and hypotheses in the scientific community. Some propose that the information is preserved on the event horizon itself, encoded in a two-dimensional format, a proposition referred to as the holographic principle. Others suggest that information may somehow escape black holes and be found in the Hawking radiation emitted by these cosmic giants. A famous thought experiment highlights this paradox. Imagine a spacecraft crossing the event horizon of a black hole, carrying an advanced AI that records all the data of its journey. Once inside, all signals from the spaceship to the outside universe cease, creating a tantalizing question: if the AI could survive and somehow transmit its findings, would it still hold the full information of its initial state? Or would it be lost forever? This question reinforces the ongoing discourse around the reconciliation of general relativity and quantum theory, as scientists attempt to address the fundamental principles of nature itself. Researchers like Juan Meldacena and others have explored the concept of entanglement entropy to further probe this paradox. Their work suggests that black holes could link to quantum entanglements with other regions of space, potentially offering a glimpse into how information might be conserved. Scientists are not only trying to solve a riddle but also looking at practical implications of this knowledge. If we can grasp how black holes operate at the quantum level, we could redefine our understanding of gravity, time, and the universe itself. This leads to exciting lines of inquiry. What if black holes are not the end of the road but gateways to other realms of existence? As researchers grapple with the implications of the information paradox, it becomes clear that black holes are not just cosmic vacuum cleaners, they are fundamental to our comprehension of reality. The journey into these enigmas continues, propelling us toward uncharted territories of theoretical physics, where the true nature of black holes and their connections to information, spacetime, and the universe await final elucidation. As we consider the cosmos, we must confront the unknown, what will emerge when the veil of mystery around black holes is finally lifted? Black holes are not merely cosmic anomalies, they are architects of the universe, playing crucial roles in its evolution. From the very outset of cosmic history, black holes have shaped galaxies and influenced the growth and formation of stars. After the Big Bang, matter began to coalesce. The gravitational pull of black holes significantly affects surrounding star formation, resulting in complex dynamics that govern the evolution of galaxies. Observations reveal a stunning correlation between the mass of supermassive black holes at the centers of galaxies and the overall mass of those galaxies. This relationship hints at a symbiotic connection. Each black hole seemingly dictates the growth and evolutionary course of its host galaxy. Active galactic nuclei, powered by these central black holes, fuel tremendous outflows of energy. These jets of high-energy particles can travel vast distances, impacting star formation in surrounding regions by heating up gas clouds and regulating star birth. A landmark study from 2000, involving the galaxy M87, provides astounding insights. Astronomers found that the supermassive black hole at its core weighs approximately 6.5 billion solar masses. This discovery yielded profound implications. It suggested that as galaxies evolve, so too must their central black holes. This interplay has led researchers to speculate on the early universe, as countless smaller black holes may have contributed to the growth of the first galaxies. But the narrative doesn't end there. Black holes also influence the cosmic web, the vast, interconnected structure of the universe. As early galaxies merged and interacted, their black holes collided, creating ripples through spacetime, later detected by gravitational waves. The waveforms reveal black holes dancing through the cosmos, carrying tales of cosmic evolution deep within their gravitational embrace. Additionally, black holes are thought to serve as the seeds from which stars and galaxies emerged. Theoretical physicist and cosmologist Alexander Vilenkin has suggested that primordial black holes could have existed just microseconds after the Big Bang. These black holes might have provided the gravitational anchor that helped clumps of matter coalesce into stars and galaxies, significantly influencing the very structure of our universe today. The quantification of black holes' role in cosmic evolution is still unfolding, with new technological advancements allowing astronomers to peer deeper into the cosmos. As more data emerges, the narrative of how black holes orchestrate cosmic growth is becoming ever clearer, revealing an intrinsic connection between these enigmatic entities and the universe itself. As we venture further into the observations and studies of black holes, we encounter tantalizing possibilities. Could black holes themselves evolve over cosmic timescales, adapting and changing just as the galaxy around them does? The further this research unfolds, the more we confront an intricate web of cosmic interactions, where black holes stand at the very forefront of creation and destruction, shaping the universe as we know it. The quest to understand black holes is a tale steeped in innovation, daring, and determination. For decades, black holes were a scientific theory, a hypothesis born from Einstein's equations of general relativity. Observing these elusive entities is no simple task, as they do not emit light. Instead, the evidence for their existence arises from their gravitational influence on surrounding matter. The journey to uncover these cosmic mysteries has led astronomers on